Okay, so now that we've gone over the parameters and components that you want to look out for in your model, I'm going to talk a bit about sensitivity analysis. And so this is something that you're going to do with your model, and it'll help you figure out which parameters you're really going to want to focus on and which ones you're going to try to get more information on, either through auditing the building or through doing more just research on what's a good range for parameter values. So this is just sort of an abstract model, just general, whatever you're modeling. You have a series of inputs, and those are going to come from known parameter distributions. In this case, I have three normal distributions, here, here, and here, and also a log normal distribution. And your input value, you might know, lies within a specific range of that distribution. So some you might be pretty certain on that they're within a small band. Some you're not so sure, and they might have a larger band. You have a specific value from that distribution. You put those into your model, and it produces some output. So in particular, we want to know which inputs are the most significant ones, or the ones I should really be paying attention to. There might be some where, even though it's a really small parameter range you're drawing from, it's really significant and it changes the output a lot. There might be others which there might be a pretty wide range which it's drawn from, but it doesn't affect the output that much, so you're okay with using a default value. So one way to help identify some of these in building energy simulation is to look at what are called component load contributions. And there are some tools in Energy Plus, and if anyone has questions of that, you can contact or email Dr. Schrabrick or us at the Building Science Group, and we can show you how to do that. But basically, it allows you to determine of the cooling and heating loads you have in your building, what are the sources of those loads. So for office buildings, for cooling load, a common source of that is the interior lights, the interior equipment, and the solar heat gain through the windows. So that's most of it. So you can expect that if you're seeing your cooling load and electric use in the summer as being pretty far off, then, well, it might have something to do with my solar heat gain through the windows, or maybe my lighting value or schedule isn't correct. For the heating load, you see a lot of it's conduction through the windows, connection through the walls, and again, the solar and the lights help us with the heating load there. So if your steam use is a bit off, things you might want to look at are, oh, okay, well, maybe it's my wall U values or my window U values that I should look at. It could be infiltration as well. That's a small piece of it. Or it's, again, the solar or the lighting loads in those schedules that we need to pay attention to. So there's a few ways you can run sensitivity analysis. The simplest one, and pretty common, is to do what's called one factor at a time. So you take sort of a default value for all the parameters in your model, and you pick one parameter that you want to vary, and you vary it by a certain amount, say 20%, and you see what percent the output changes. So you vary, let's say, wall U value by 20%, and you see what happens to the total energy use. Does it go up by 20%? It's probably not. It probably changes by a bit less than that. But you can compare that sensitivity across different parameters to figure out which are the most significant. Very important things with this are that it's only local. So you might have a different set of parameters that constitute your model, and the sensitivity is not going to be the same if some other parameters are equal to different values. So you have to be very careful with that. And it doesn't account for, therefore, interaction between parameters. So an example of that would be you have a window-to-wall ratio in your model, and you also have a wall U value. So we would expect that if the window-to-wall ratio is much larger, say 80 or 90%, then the wall U value is going to be much less significant than it might be if, say, the window-to-wall ratio was 5%. You might not necessarily want to use percentages. I recommend using standard deviations on that parameter distribution if you can. An example of that is if you have a boiler efficiency of 0.88 and you vary it by plus or minus 20%, well, then you might get an efficiency value of 1.06, which is infeasible. So if you have a parameter distribution that you know you're sampling from, then you can pick, say, a standard deviation of that. But that requires you assume some sort of distribution. So if you want, you can assume a normal distribution or a log normal distribution. Those are probably the most common, or a uniform distribution. Another way to do this sort of local one factor at a time analysis is just use the partial derivative. So in this case, you'll just be making a very, very small change. So maybe 0.1% on some certain parameter and see how the output changes. And you could do your sensitivity analysis that way. The last one that you can mention, which is also a local method, is the sensitivity index. So what you'll do is you'll take your minimum value of your parameter and your maximum value, and you will vary the simulation across that, and you will see what happens with y. You'll see what the maximum value it attains and the minimum value it attains. You'll subtract those and divide by your maximum, and that'll give you a sensitivity. There are lots of other global methods that are out there, and these are really what you'd want to use, although that's beyond the scope of what we expect you to do in this course. One is an obvious one that people use all the time is just regression. So you regress your output, your y value, generally total energy use, to all of your input variables, and you see which ones have the best regression coefficients, which is saying that they're pretty important in the model. Or you can use what's called a partial correlation coefficient, and you can read up on that if you're interested in using that approach. There are some more formal statistical methods you can use. A few I should mention here are analysis of variance with blocking or factorial designs. So you either have discrete variables, which you would use with blocking, or factorial, where you're changing, say, a continuous variable, and you're interested in seeing how those parameters interact across the range of their values. And so there's different statistical tests you can use to do that. One particular one I want to mention, which is pretty widely used in the building energy simulation community for researchers, is the Latin hypercube sampling. And so the way that that works is, say we have sort of two parameters, x1 and x2, and we have their cumulative distribution function. So this is the distribution of, as we increase our x value, how much of all the x values have we gone through, and so that'll eventually go up to 100% at our maximum x value. We can break that into, say, 5 different regions here, and we'll take our x2 value and we'll also break that into 5 different regions. And we will, instead of just sort of sampling randomly from both of these variables, we'll just sample once in each of those divisions. And we will then randomly pair those groupings to create what's, in this case, this is a Latin square design, where you have these different bins, or divisions as they're called, for parameter x1 and x2, and we've matched these here. And this will give you a pretty good picture of the variation that sort of exists in your model, and you can use the statistics you draw from that you can use all your outputs from that to draw different statistics of variance of your model output based on these parameters. If you want more information on this sort of design of experiments or sensitivity analysis, NIST Engineering Statistics Handbook has got a lot of good information there. There's also a sort of recently published review on sensitivity analysis in building energy method or energy analysis and building energy simulation if you're interested. So particularly for our class and for sort of the type of buildings that we're modeling, which are sort of education, office, classroom buildings, you're going to want to focus on parameters that are, one, energy use is very, very sensitive to that parameter. And the second is that you're sort of uncertain as to what the value for that parameter is. So it's got a wide range of values, and it's something that if it varies across that range, then the output's going to change tremendously. So for commercial office buildings, and to some degree educational buildings, those variables are going to be your temperature set points and the setbacks that you have. the plug load density and the schedule, which is occupant related, the lighting load density and the schedule. Then on the HVAC side, the fan supply air temperature, the fan static pressure rises, and the schedules that those are operating, as well as exterior lighting density and schedule if that's present in your building. That's generally for parking lots, which might not be as applicable for the education buildings. But if they do have that and that's metered, then that's very significant. There's other ones here which the parameter range, usually you know this value pretty well, but if you don't, and the value could be very different from a typical default value, then you want to get more accurate information on that. Examples of that are the heating equipment efficiency, the cooling equipment capacity and efficiency, all of your U values, or R values, so in this case the wall and the window, R values, the solar heat gain coefficient, the window to wall ratio. Generally you can ballpark it to about 20%, but it may be plus or minus 10%, which is actually a very big difference, so you want to make sure that that's a bit more accurate. Infiltration is a pretty widely varied one, which we had talked about before, and the outdoor air minimum and minimum flow rate for the terminal boxes for your duct system. So these are all parameters that I suggest you look at, and if you can get into the building and just even slightly narrow down your expected, what you think your expected range for this these parameter distributions are, then that will greatly improve the accuracy of your model.